There are probably copies, I hope there are copies of Stardust back there, if anybody doesn't have one.
A whole bunch of them.
Okay. There are no planetarium shows anymore at Montgomery College because the planetarium has been shut down until we get a new building, and that won't happen until the fall of 2022. And the American at Senior Physics Group is having a meeting. When is that, Jack?
It is this Wednesday, the 16th, at 1 o'clock at the American Center for Physics. They're next to the College Park
And
Metro.
what's the subject?
The biophysics of life in extreme environments.
We'll make sure you can grab everything.
Toshiko Ikei from Georgetown University.
And next meeting, we're having the lecture is on lava tubes of Mars. But Elizabeth is very worried that there'll be a huge crowd to show up for that talk because there's also going to be a book signing. So I'm urging, while I parked in this parking lot tonight, next week I'm going to park across the road in the administration because they have an infinite. They have a lot of parking over there. So if there are any late arrivals to the book signing, and this parking lot here is kind of small, so we can be polite.
Are they gonna bring books too?
What's the
I
book?
think so. It's in the, I don't remember the fellow's name, but anyway,
It's Antonio Paris.
yes, I know pretty, so he will have books.
And you
So, I
can
mean,
buy the book from him?
Yes, he's very entrepreneurial.
Oh, okay, all right.
So he's written a book, and the subject of his talk is also going to be about lava tubes on Mars. So, maybe you can buy the book after his talk if you think he'd get a really good talk. If he does a crappy, as almost all of our speakers are good.
They're all good, just some are better than others.
Some are better, yes. Gooder and best. And I suspect our speaker tonight is going to be one of the best of the best. So are there any other announcements that need to be made? Okay, yes.
One thing.
Oh, we need to vote on something too. I'm glad you stood up.
Okay.
One thing is, wanted to remind people that.
Can you come up front so? we
Sure.
can walk
Yeah,
in here?
so we can see you.
We'll see you and hear you.
Hi, I'm Guy Brandsburg, and I'm the current president of the Hopewell Observatory, which is out I-66. And we're having an open house on Saturday, 2 weeks from tonight. And you all are invited. And here's a little handout that shows how to get there and so on, if you'd like to come. I will warn you, it's out in the woods, and
Up a mountain?
on a mountain, and the road isn't the greatest, and sure, I don't need to keep any of these.
Okay, I'll just take them.
Yeah, so,
Awesome.
oh, and also, we don't have running water, so we have an outhouse, and we have bottled water and, kettle for tea and coffee.
They do have electricity.
We do have electricity.
Lights, but they try to keep the lights down because obviously that's how you see stuff.
And if it's cold, we have a nice warming cabin so you can get warm there. We have a couple of telescopes of 14-inch diameter and a new mount that we've made, and it's fun. So if you'd like to come, that'll be October 26th, 2 weeks from today.
And society needs to vote on one thing. We have a telescope that we own that we would like to see actually be used again. Guy has repaired it, and it works now, and he's got the, all good refractors have lenses that have to be matched and turned the right way, so it now really works really, really well.
It
So-
works pretty well.
Pretty well.
I haven't actually taken it back out and put it on star test with everything, but it looks like it's gonna work,
Okay.
I think.
So, it's been suggested that we sell it to the Hopewell people for $1. So that's the motion that I make. Do I hear a second?
Second.
Is there any discussion? Does anybody want to raise the price? It's, if you had to buy it, it'd be worth more, but we want, telescopes that are not used are worthless. This will be used, and it'll be used to benefit all of us.
Right, and it's been sitting in what used to be the trail across the parking lot for 11 years.
And it hasn't been used at all.
Right.
Oh.
And,
What's the aperture?
it's 6 inches, and it's f/14, so.
It's pretty long too.
Yeah, so 7 feet long. It's heavy. It has
Brass.
an antique brass mount, but somehow the counterweight shaft got lost. So that means that somebody has to machine, probably me, machine the shaft and so on and so forth. So it's not really yet usable.
But soon will be again.
Yeah. There was actually some grumbling on some of the members of my observatory. We really want this. This is going to be a lot of work. But I will try to put it into operation and machine the counterweight tube and so on and so forth.
Now, we also have at Rock Creek Park. When next is that?
Exploring the sky.
Exploring the Sky. It's on the NCA website. And Jay Miller's not here, but we had a lot of people show up and a lot of telescopes and a lot of things. And there were a lot of people looking at stuff because it was clear.
Well,
And,
actually, this last time I went and it was not clear.
Okay.
It was clear in the daytime and then it completely clouded up. So we told people to go home.
Right. But, yes. It's November
The
the
final Exploring the Sky is Saturday, November 2 at 7 p.m.
at 7 p.m. because it's getting dark sooner. All right? So, you've heard the motion.
I
Yes?
call the motion.
What?
I call the motion.
Okay. Call the motion. All in favor of selling it to Hopewell for $1, please say aye.
Aye.
Raise your hand.
Okay. Is there any nays? Okay, so it carries unanimously.
Okay. I have the bill of sale.
Okay, I'll sign the thing as the president of NCA.
Check it on the-
Now it has my, are there any other announcements before I can shut up and turn it over to our vice president who will introduce our wonderful speaker? Okay.
It's a very great pleasure to introduce our speaker tonight, Duilia Demel,
now.
and also her husband, Tommy Wicklin. Both are astronomers at Catholic University. They do very interesting research. Duilia got her PhD at the University of Sao Paulo in Brazil, and then was assistant professor at Chalmers University of Technology in Sweden. Then she did postdocs at the Hubble Space Telescope Science Institute, the Cerro Tololo Inter-American Observatory in Chile, the National Observatory in Rio de Janeiro, Brazil, and then she became a Catholic University of America researcher at the Institute for Astrophysics and Computational Science at Goddard Space Flight Center. She then joined the physics department at Catholic University, where she's now a full professor. Her research concentrates on the formation and evolution of galaxies. And the tools she uses are the Hubble Space Telescope and large telescopes such as those in the Gemini Observatory. She's a member of two of the Hubble Space Telescope's research teams, the Hubble Ultraviolet Ultra Deep Field team and the Hubble Candles team. And she uses Hubble to investigate, one of the things she does is use Hubble to investigate how the disks of disk galaxies form and evolve. And she also studies colliding galaxies and how they affect the intergalactic medium. Her most recent discoveries are the existence of dozens of things called blue blobs that are associated with these collisions, and that's what she's going to tell us about tonight.
Thank you. Well, first, thank you so much for having me here. It's a pleasure. And I feel almost a little guilty that I haven't heard of this place before, and I have never been to the observatory before. So, as John was saying, I am a professor at Catholic University, and I've been here for quite a few years. And I'm currently the Vice Provost for Global Strategies at Catholic University. And Catholic University is not so far from here, so I invite you all to come visit us too. We have a great presence at NASA Goddard, and you may have seen me around probably when I was a little bit younger. So today what I'm telling you is really a research I've done with so many people. And you went to sleep? And I have here a list of names of people that have collaborated on this project with me. And the ones that I have stars next to it, it's because they are really the stars in the projects. They are our students, they're grad students. All of them are now doctors. But they were students when we started this project, and this became part of their thesis. So here on the background, I'm going to show you this image again, and you'll see it again, and we'll go over it. So especially for people who don't understand how research gets done and how astronomers decide on their projects, let me tell you a little bit how we decide on projects that became what this project. This project has about 20 or so articles, peer-reviewed articles, but it took a long time for this project to get going. So how does it work? And I'm going to give you that feeling as well. So my PhD thesis was in interacting galaxies. Galaxies that are colliding. In particular, galaxies are very close together. They are in what we call compact groups of galaxies. And a friend of mine, her name is Claudia Mendes Oliveira, she's also from Brazil. She did her PhD in Canada. And she worked with the father of compact groups. They're called Hickson compact groups of galaxies. And Claudia and I were in a conference together when for the first time we saw images that a little tiny satellite was producing. And this little tiny satellite is called Galax. So Galax is an ultraviolet satellite, this big, it's only 0.5 meter across. And Galax is not operational anymore, but he was such a productive satellite. So Claudia and I are sitting together, we are seeing the first images. This is like in the early 2000s, and we saw this image, maybe 2006. So we saw these images and we were like, wow, that is so cool. Maybe we should look at compact groups of galaxies with the satellite. Because when we look into the ultraviolet light, what we are seeing are the young stars. The stars are the baby stars, stars who are just born. They will emit in the ultraviolet. So it's a very hot and energetic light. So because interacting galaxies promote star formation, we thought, wow, in the ultraviolet they will look really interesting. So then, she went to Brazil, I came back here, and at some point I started thinking about that too, and then we decided to go and start applying for Galax Time, start applying for archival to look at the data and all that. Meanwhile, I was talking to two collaborators of mine, Jay Gallagher and Linda Smith. Jay Gallagher was a professor, now he's retired, but he was a professor at the University of Wisconsin, Madison. And I told Jay, have you seen ultraviolet lights from the satellite and how interesting they are? And maybe we should look at your favorite galaxy. So Jay's favorite galaxy is this one here. It's M82. Does anybody familiar with M82? Yeah. Yeah, some are. M82, actually I saw a poster here that has M82 there. So it's this one here. So M82 is what we call a starburst galaxy. So it's a galaxy that produces a lot of stars at the same time. So I told him, look at M82 with galaxies, and he said no. So I told him, let's go look. And then we started looking, and I realized that because Galax is such a small satellite, it has a very large field of view. So lots of objects in the same field of view, Galax saw it all. And it saw M81 and M82. M82 is here, M81 is here. So the ultraviolet light is 1500 angstroms. I know it's kind of get a little bit technical here. That's the near ultraviolet light, the far ultraviolet light. It also has the near ultraviolet light, so it has two filters. So this is a composite of these two filters. But M81 and M82 have a companion that sits over here that you don't see. And the reason you don't see is because we usually don't point at it. It's NGC 37.7. It's a very bright, it's not a very bright galaxy, it has a very bright star of the Milky Way in front of it. So we usually don't show NGC 37.7 because it will damage the detectors. So, or here we have M82, M81, the one that we don't have, it's a triplet. Then in parallel, I was studying with Claudia the complex group 100. I'll show you how it goes, I'll show you results of those and why then it became this mega project that we have 20 papers out of it. First, let me show you an image that's actually an amateur image. This is not a professional image. This is a famous amateur. You can get his stuff online of M81 and M82. And here is the galaxy ultraviolet image. I don't know if you can see for sure, but there is something that catches your eye here.
Yeah.
That here is not so much, right? Can you see that?
No, can't see anything in that.
So there's something that's kind of dusty here. Well, in the ultraviolet it's really bright, right? So what is that telling us? It's telling us that we are seeing a lot of baby stars here that we don't see here. Because this is just the optical, the light we see with our eyes. So, it's already a good hint that galaxy is going to tell us some interesting phenomena happening here, right? Then, because of our background in galaxy formation and how galaxies evolve, we know that when we look at interacting galaxy, we also have to look at the gas around the galaxies. Because when interaction comes, it becomes almost like a ballet, right? They go around each other, gravity puts them kind of orbiting each other, and they go past through each other. And gas takes a long time to react, so stars go before and the gas continues. So gas is also left out, like in a debris outside. So when we look at the same triplet, and now you will see M81, M82, NGC 37.7, this is not an optical image, this is the neutral hydrogen image of this triplet. And it's taken with a very large array in Socorro, New Mexico. Just for you to have an idea of the distance to this object, it's at about 12 million light years. So it's very nearby. And that's why we can do all this work we did with this particular triplet, because they're so close to us. All right, you will probably remember the fuzzy little one that I showed you that didn't show in the optical image. It's over here. But you probably do not remember seeing anything here. Yeah, it's because there wasn't much there. So here they are, and now what I discovered was this. So right at that, it's called ARP's loop, because Houghton ARP had already seen some signs of star formation in the area. And with galaxy, we actually saw what we call the blue blobs. So these are the blue blobs. I know. So what are they? Well, then I won the lottery. I went into the Hubble archives, and I found out that actually Hubble had observed this area of the sky. Remember, Hubble field of view is also very small. So it's not like we have Hubble images of everything. It was just a coincidence that Hubble had seen that area. So when we look at this area, for instance, this is one of the blobs. Baby stars. Here's an interesting case where we see stars, but we also see some galaxies in the background. So the ultraviolet light here is only from these two blobs, and this is this and that. These are not in the galaxy image. They are in the background. And here are the bright ones. Again, what's red is in the background here. And this is the entire image of that square that I showed you of galaxies. This is the Hubble image of that area. Except that it's cut here, but you'll see. They're supposed to be there. And I love that one. The last one that showed up, I'm gonna go back one and you see again the blobs popping up. And here is an association that shows up really cute. So what are these things doing there in the middle of nowhere? So that's the question we're asking. So now it gets a little technical, but you're all gonna become very good at this. All right, ready? Let's go. Color magnitude diagrams. So what does a color magnitude diagram tells us? Tells us the stellar population. So when we look at this image that I just showed you, this image, you see stars, right? Now what we did is we identified each star in this image, and I'm not kidding. So you go and you identify each star on this image. You measure its magnitude, its brightness, and you do that in 2 filters, so you have a color. And then you plot magnitude against color. And when you do that, you have models of stellar evolution that's going to tell us the age of those stars. That's what this plot tells you. So the color over here, the magnitude over here. And we do this with Elena Sabi from the Hubble Space Telescope Science Institute. So when we look at this area here, where we call them the blue main sequence. The blue main sequence, so let's pick a star. Here's a star of magnitude 24, which is relatively bright, of this color, which is very blue. And it sits over here, and stars of this type have approximately 7 million years of age. So, and we can do this, we do this for all stars, and we find a lot of young stars. Just remember that our own sun is 4.5 billion years old. So now we're talking millions of years old. So these are really baby stars. They're young stars formed just a few 100 million years ago or so. So this was for us very interesting that we could see even the ones that are old and not that old. And then we separate them by objects, by the different blobs. And then we can actually see that a population of 10 million years would fit one of the blobs. A population of 30 million years, a population of 10 million years, of 25 million years. And there they are. So each star here is 1 point on this plot. So we could actually trace the age of every star in the blobs. We are doing this because we're trying to understand why they are way outside there and not inside the galaxies. And then our questions was, were they born outside the galaxies? Or were they ejected out there because of the collision of galaxies? That was the question we were asking. So we measured the luminosity in the ultraviolet by just collecting the photons in the ultraviolet and measuring their luminosity. We also went to this telescope, it's the Wind Telescope in Kitt Peak in Arizona. It's a 3.5 meter telescope, and actually I didn't go, it was actually through collaboration with Linda Smith and Jay Gallagher. And the blobs are these things here that you're seeing. And we observed it in the H alpha. So now we have a hydrogen filter that is very narrow. It's only going to capture the light of very young stars. So we observed them, not all of them emit in the H alpha, not very bright in the H alpha. So what we did, we combined all this luminosity and we compared that with the Orion Nebula. And they are equivalent to only 5 Orion Nebulae. So if you look in the ultraviolet, so if you look at that area in the sky outside M81, that's equivalent if we had there 5 Orion Nebulae. So it's not a lot of stars. That's why we call them blobs, you know, the blue blobs. They are superstar clusters, associations of stars. And we believe that they are formed out there. We have reasons to believe it, and one of the reasons is this little video here. So this is a simulation. It's from Min Yoon's website. He just put it there so you can pick it up too. where we see when galaxies start, it's already getting a little ugly, old.
So that's three galaxies colliding?
Galaxies colliding. So here is NGC 37.7 coming in, M81, M82. Oh, actually the other way, right? Yeah. So
What's
this
the
is
time scale for this
M82.
whole thing?
Yeah, it started at time 0, and then we let it run for about 200 million years. So 200 million years later, this would be the time that we see. So do you want to see it again?
Yes.
Yes.
So there you go. Now M82 is coming to the place, the yellow one. And then they pass through each other. And then I want you to pay attention what happened in between them. Ah, stuff out there, right? I'm going to have a zoom into that area now, and you see. There we go.
Oh, wow.
When I saw this, I had a Archimedes moment. You know what I mean? The Eureka kind of thing. Wow! This is exactly what's happening here. So this is the gas, though. It's not the stars. But we know that there are stars here, and we know that there are stars here. So it's explaining pretty well that what happened 300, 200 million years ago caused what we are seeing today. So the problem now, and it gets a little bit technical here, so just bear with me. What happened here is that area, remember this is all hydrogen, it's neutral hydrogen here. The density there is very low. So when the density is very low, how do you form stars? Because in order to form stars, you have to have a high density molecular cloud that will collapse and boom, form stars. How would it happen? How can we do that? But we know the stars are there, so they formed. And we know there is gas there, so there is matter that will form stars. So we started doing some research on this, and there are some theories that propose that if you have a little bit of turbulence, and the turbulence could be caused by the interaction. So you have a little bit of turbulence in that, even if it's cold there and it's not very active, the molecular clouds are not very active, just a local turbulence will be able to form stars. So that's how we could justify that, and that's what's written here. So you may recall we talked about this little one, but I kind of forgot and didn't mention anything else anymore. But now I'm going to talk about that one. So just remember, I used Hubble to look at that area. So I also used Hubble to look at this Holmberg 9 galaxy. Remember, Hubble is above the atmosphere, right? So Hubble can actually separate the stars. You can actually see individual stars. Telescopes from the ground, not even the giant ones, can do that. So it's just really particular for Hubble that we can see individual stars at this distance. So we look at Holmberg 9, and I know and John also seen this image because I sent to him, and it's such a beautiful image. But of course here with the projector it doesn't show as beautiful. But there are a few thousand stars in this little tiny galaxy. And it is the nearest young galaxy here. So it's a young galaxy with stars of less than 200 million years, and is the most nearby young galaxy. And
How
this is
far away is that?
it's the same distance as M81 and M82, so it's at going back.
12 million light years.
Yes, 12 million light years, right? I just don't remember in light years, so I have to go back. And I'm going back. It's 3 megaparsec.
Next one, tell us.
So 12 million light years at 3.6
Oh, okay,
megaparsec.
okay.
So that's why you go put some animations. There you go. So the same distance. Now we did the same thing, the color magnitude diagram. We look at that. Now you see many more stars than the previous diagram, right? Because now we have a lot more stars. Here we have the isochrones, which are these fits here. In blue, we can fit a stellar population of 10 to 200 million years, which is about the same age of the blue blobs, right? But we have a population of old stars too. And now we have a population of stars that can be all the way up to 12 billion years. So what's happening? I know. So what's happening? What happens is that this area here where this galaxy sits is very close to M81. So during the collision, stars from the M81 end up here too. So we have stars from this galaxy. This galaxy has old stars because it's a regular spiral galaxy. And this galaxy here has young baby stars plus old stars from the parent galaxy, we call. So this little dwarf galaxy here, we call it a tidal dwarf galaxy. And the word tidal has to do with tidal interaction, because gravity is really what's driving the interaction here. So Hubble was able to separate them. So here are the results from Humber 9. Two populations, young stars of less than 200 million years and older stars from M81. And there she is, and there is, and this is better now. So that's Humber 9. All right, and I told you this was a pilot study that we were doing. So I did that with this team, and now I'm doing this with Claudia and our other team. And we're looking at a compact group of galaxies. I know the image is not so beautiful, but it's on purpose. So here is an image that is a combination of images. Remember, I told you the galaxy was a 0.5 meter ultraviolet little satellite. And you know, as amateurs, as you are, that it's small, it's not so good, right? You want a bigger aperture, you want a bigger mirror, and otherwise your resolution is low. So although we use the optical data is the CTIO 4-meter telescope, we have to degrade the resolution of the CTIO 4-meter telescope to match the galaxy 0.5 meter telescope. And that's the image we have combining the 3 filters. It's going to get nicer now. Remember when we looked at the previous example, we have the gas around it. And that was key for us to find the blue blobs, right? So we need a map of the hydrogen gas of this group. And it's amazing. Ta-da! So it's way out here. It goes this, the group is here, right? 4 spiral galaxies, they're right here. This is the group. Now when we put the gas comes all the way here, more than 424 kilolight years, thousands of light years away from the parent galaxy, you have gas. But what are the blue blobs? Well, they are there. Can you see it?
Yes.
Yeah?
They're even further.
Yeah. So they are here, inside here. Just put them here so you can see. But they're actually inside here.
I understand.
And this is inside here. So the blue blobs are there. And then I use a Gemini 8-meter telescope, and this is a proposal we put together to observe this compact group of galaxies, and we got these images. They are little dwarf galaxies. But now remember, Gemini, first this one is much further away, and I'm going to put it back here because I never remember distances. The other one, remember, was 3.6. This is 76.3 megaparsecs away, so it's much further away. Not even Hubble can see the individual stars of these galaxies. So it sees the composite of the stellar population. So Gemini can only see the composite too. So what did we do? we did spectroscopy of the dwarf galaxies. So we put a spectrograph on here. It's actually a very, how do you say, laborious work, so you have to do this with fiber optics. So we get the spectrum and of this individual object, but it's the integrated population of stars.
On that last picture,
Yeah,
is that graininess in the background, is that basically
you mean here?
electronic noise? Or is that, we have stars and stuff?
No, it's noise.
Okay.
Yeah. So the stars are, this is a star, and these are actually galaxies. This is a star. This is a galaxies and stars combined. Stars of the Milky Way and galaxies in the background. And here's a little dwarf galaxy that has a little bit of a plume here too. So we get the spectrum of this object. So now what does the spectrum tell us? Well, the spectrum tells us the chemical elements, the chemical composition of the entire stellar population. And from the spectrum, we can actually tell the metallicity of this object. What does it mean? So an object that has very high metallicity, it could mean two things. It could mean that a lot of stars have been born, many generations of supernova, they have exploded, they have enriched the gas, and you have more metals in the gas, and you form a new generation of stars, and it's very metal rich. For astronomers, everything that's higher than helium is a metal, but that's another story. So anyway, so it means that it's an old generation of stars that's gas is being reprocessed in that area. So how do we know that? Because we measure the metallicity. So I know this is a busy plot. I don't want you to look at all this. This plot is only to show you the following. Here we have luminosity, brightness. Here we have metallicity. So how many metals we have. We're comparing with the oxygen metallicity, okay? When we look at this axis here, the crosses are dwarf galaxies in our neighborhood, like the large Magellanic Cloud, the small Magellanic Cloud, Leo, galaxies in our neighborhood. And when we look at the two little galaxies of the previous group, they sit over here. They're much more metal rich than these ones are, and they sit in a completely, totally different area of the diagram than the regular ones do. So this is just for us to evaluate the history of these galaxies. So this is the results from the pilot projects. So M81 and M82 contain young, low-mass superstar clusters and also Homburg 9. That group that I just showed you, and another group that we also, Claudia in particular, studied, they have these young, massive, tidal dwarf galaxies, but they don't show any sign of those small blobs, those associations like Orion. And then we start thinking, could this be because the environment of a compact group is very different from a triplet? Could that be what's causing it? And this is what triggers astronomers to keep trying and going and going. There's always a question, right? So how would we address this question? Well, we decided, we need a sample of groups and a sample of other interacting galaxies that are not in groups, and compare them. And that's what we did. And NASA gave me a lot of money to do that. So we found these two environments. One of them was a compact group, another one was an interacting galaxy with these H1 tails, the tails of gas. And then we use all kinds of telescopes to do this. And so here is a compact group of galaxies. So galaxies are really close together, and they show signs of interactions. They're distorted, they're peculiar, because the gravity keeps pulling them. And this is Sergio, a student who did most of this. So Sergio picked the sample, and this is Claudia, my collaborator. And here's a bunch of those. So these are ultraviolet images. That's why they don't look so nice, because this is like what we see when we get data. So and then we start identifying the blobs. But we want blobs inside an area that we are looking at, so that's why we have this diameter around. And we can tell this one has many, has quite a few of them, about 15. This one has few, there's only 7, 9. Here we have another one with quite a few, and there's much less here. So there are not so many of these little thingies that we are identifying them. So we start thinking why. The result of this comparison was that some of the groups, they're very close together. The galaxies are really close together. Some of them have even merged with each other. So we found that groups that have more of this advanced stage of interaction, they have more of these UV sources. So the one that I said many here, they are more advanced. And then they have more of the UV sources in the medium, and they have similar luminosities of the tidal dwarf galaxies that we found before. You know those little ones that we look at Gemini? We start finding them in groups. We found them in that group too. So we said, okay, let's look at the interacting galaxies. They're not groups, these are interacting galaxies, 2 or 3 at most. Have 25 of them. Remember, we always have to have the neutral gas, the hydrogen, because we're going to look inside the gas to look for the blobs, right? So these are the maps in the hydrogen maps. And then we did a website. And we have here a lot of these galaxies with tails. This is all of them. And the data we got. And this is part of Fernanda's thesis, actually. So Fernanda observed a bunch of these galaxies and identified 189 blue blobs out of all the 6 galaxies. And then we compared with M81, M82, and the 2 compact groups. This one is particularly pretty, right? So you can tell it's a galaxy that has gone through an accident. Here's another one that's really pretty too. And that's another one. They start showing some weird things, like what the heck is this? So interaction does that to galaxies. So I chose this one in particular, but I have data for all this. It's being published in 2012, 2014. So this is NGC 2623, which has this weird format. It's kind of peculiar shape. But we're not studying the galaxy itself. Remember, we're studying the hydrogen that's out there and the blobs that are inside them. So this is the hydrogen that's out there in red. The blobs are this and this. So we did this for all these galaxies, and we studied them, and we find 37 blobs. They have ages of less than 100 million years old, so they're very young, they're babies. But on average, they are less massive than those ones that we observed with Gemini. So they're different. They're young, but they're not massive. And here's more of them. Now I'm going to show you one that's one of the most spectacular mergers. So what happens, galaxies go through these collisions, right? At some point they will merge together and make one galaxy. So this merger that I'm going to show you is this one here in NGC 2782. And here is a Sloan, you've heard of the Sloan telescope? Yeah. Some have. This is a Sloan image of that merger. And you see it's kind of weird, right? A little bizarre. It's not elliptical, it's not spiral, it's just a mess. And it has something here, right? Can you see that?
Yeah.
All right, so now you're going to be surprised because the gas is actually not here, but here. There it is again, and in blue is the gas. So gas is way out here, which is bizarre, right? So gas, as I said before, it takes time for it to react. So, so we went also to the Vatican telescope in Arizona, and we got this H-alpha image. So it's a very narrow band, a very narrow filter. So only the light from the very young stars will pass in that filter. And we also identified the blobs in those images. So here we have the H1 tail, the blobs are in circles here. And then Gemini is our friend. So the Gemini telescope in Chile we used. Unfortunately the quality here is not so good, but most of them we are able to resolve in little stellar clusters. This one in particular you could see if we had more light here, but so we see the similar things we saw before, that they are either dwarf galaxies or stellar clusters. Here's just the H-alpha image. So what we did with Gemini again, we took the spectrum to learn about the metallicity. Because remember, the very first ones when we had the age of the blue blobs of MA1, MA2, how did we get to know that the metallicity at that point? We did not have spectra of them, because you can't. Because Hubble would not be able to take the spectrum, they're too faint. So at that point is by that fit of that I told you, I call it isochrone. I don't know if you heard when I said the isochrone. So that fit that gives us the age gives also the metallicity. So how many metals there are there. Here with Gemini, we take the spectrum because we cannot resolve the individual stars. So anyway, 7 objects, the ages are really young. The mass is not so large. So Gemini images resolve them in several objects, but we don't find those tidal dwarf galaxies that we found before, because these are not groups. These are just interacting galaxies. So I don't know if you are already getting it, that there is a major difference between them. So here's a bunch of papers we published. Every time we found something really spectacular, we published it in a variety of journals. So these are the main results. So interacting galaxies, including one merger, which was the last one I showed, lack the massive tidal dwarf galaxies, which are usually about 0.1 million solar masses that we found in groups. So it's possible that the group environment is responsible for the TGG formation and survival. So the potential well of the group will drive them away from galaxies and keep them there, and they don't get disrupted. So here's just to conclude, we have far ultraviolet and hydrogen gas and optical data of interacting galaxies and compact groups. And we found star formation in the H1 tails and bridges of this gas that has really low density. We don't even know how to explain how stars are there. We have young and old stars found in the same region. Some of the stars have been launched out there. Some of the stars have been born there. That's why we call it are formed in situ, sort of formed out there in the middle of nowhere. And some were ejected from galaxies and end up together with the young ones. We find this high metallicity as a signal that the object was really formed there, because then this is gas from the other galaxy that end up there already pre-enriched. So what's going to happen to these blobs? What is the fate of these blobs? Well, we don't know. We think that they can become, for instance, globular clusters. They could be the primordial globular clusters. They could become dwarf galaxies. Or they could just dissolve and become sparse star streams out there in the intergalactic medium. Thank you very much.
I thought all globular clusters were extremely old.
Only in our galaxy.
No, actually, there is a we could turn on the lights, yeah. There is a population of globular clusters that are young,
Really?
and usually they are outside these mergers. And we think they are the product of new generation of stars are born out there and are forming, they're, yeah. So if you look at a galaxy that is a merger, it could even have two populations of globular clusters. One is the old one, and one that's young one.
Other questions? This may be a little oddball, but you're pulling these stars out of the galaxy. So are you also pulling dark matter out of the galaxy also to keep things bound properly, or is this what you don't know, that you don't know whether you've done it, so you don't know whether it's going to last or not?
So yeah, this is a great question. So it's especially a great question because we have compact groups of galaxies. So compact groups of galaxies have a lot of dark matter. So the dark matter actually slows down the interaction. So otherwise, the compact groups would have already formed one galaxy. So dark matter kind of interrupt the interaction here. But what you're asking is if the star will bring dark matter when they get ejected, for instance, right? Not quite. Dark matter in galaxies are in the outskirts of the galaxies. So if they would disrupt somehow dark matter, I'm not sure. I don't think they would. But with compact groups, dark matter is crucial there because if there was, and that's probably why the tidal dwarf galaxies are able to survive in compact groups. Because that was one of the conclusions, right? The compact groups have tidal dwarfs and the other ones don't.
Because the tidal forces that pulled out the gravity, the stars, are also acting on the dark matter and pulling some of it out.
Yeah, they don't act on the dark matter because we actually don't know this relationship that dark matter has with stars. We know that the dark matter is around them, but we don't know exactly what is that will drive the dark matter if the star gets pulled out. We don't know that. What we know is that we need the dark matter there to keep things together.
Thank you.
Mm-hmm. Make sense?
Was there a question?
I was just curious about how, could you go into a little more detail about how the dark matter would affect the collapse of these?
Yeah, so this is great actually, because when I did my PhD, back in the 90s, right? Lots of people used to say compact groups should not exist. Because when we did the calculations and we calculate the speed of the interaction and everything should have already collapsed and formed one galaxy. So when we did the computer simulations, and we would do the simulations just like that triplet, we would do simulations like that, they would just collapse very quickly. So we only start understanding how interaction worked when we added a component that was dark matter. So, because the masses now are much bigger, because dark matter will add mass, right? So we kind of started trying to reproduce an image, because we see a snapshot. When we see a compact group, right, we see a snapshot of the whole thing. I want to show a compact group here that's really pretty that I only passed by very quickly. I think it's this one, yeah. So here is Stephan's quintet. So when we look at this, if we count only the stellar mass of this object, the stellar mass of this object, the stellar mass of this, the stellar mass, and then we put it together in the computer simulation, we run the clock, they will make one galaxy in like 100 million years, boom, done. But we know they're out there. So then we start adding dark matter to each of them. And then now things go much slower and we can actually
What
understand.
distribution did you assume for the dark matter?
Oh, I don't remember this.
What was that question?
What's the
What
distribution?
distribution of dark matter did you assume in your simulation?
1 over r squared if you want a flat rotation curve.
Yeah. But here it gets complicated,
Sure.
right? Because they're so peculiar.
Right.
So that simulation you showed takes dark matter into account, right?
No, it doesn't. Dark matter will be more tricky when you have 4 to more galaxies and they're closer together. That's why they're called compact. So that simulation I showed is only stellar mass. Doesn't even have gas on it.
Are there other questions back
This
there?
is speculative. Would you guess that galactic habitable zone would be larger for these compact groups than in a general galaxy?
I have no idea. So,
I'm thinking of high metallicity and not so many
stars.
collisions that you would have near in the nucleus of a galaxy.
So let's divide your question in two. So so our galaxy, right? How is it in our own galaxy? The habitable zone you're asking, right? So we have the solar system, and we know the habitable zone of the solar system. So now we go to another star inside their own galaxy, and we need to know the habitable zone of that star. So what do we need to take into account then? We need to take into account the temperature of the star. If it's a star like our sun, we know the habitable zone, where it's be. If it's different, we need to do the calculations. If it's very, very hot, the habitable zone is going to be far away. If it's very cold, it's going to be very close, right? So this works for our galaxy. Now you're asking me for a galaxy that has a lot of dark matter, is that it? Or a galaxy
No, these compact
groups?
that you have up there because of the old stars in them with high metallicity.
Mm-hmm.
Do I get that right?
Yeah.
There you have the metallicity allowing
Yeah.
for planet formation, et cetera, et cetera.
Yep.
And perhaps not as question here, perhaps not as much interference from collisions as you would get closer into, say, a nucleus of a large galaxy.
So when
So I think what he's talking about is certain parts of the galaxy would be just too dangerous to have.
yeah, so when galaxies collide, stars do not collide,
Right.
right? The fact that they're more metal rich, they have more metals, it means that their stellar population are different from the sun, or at least like the sun. That will affect the habitable zone or the planet formation even, right? So if it has more metals, when you have the disk around the protoplanetary disk, right, that will form the star and the planets around it, it will be different than here. Yeah. So it will affect. I just don't know how.
If there are no further questions, let's thank our speakers.